This PowerPoint will go over day-ahead wind speed forecasting using ARIMA models. The original paper was done by the authors listed in the bottom left corner, and the revision has been done by the authors listed in the bottom right corner, Jamie Norman and Heather Baker. You may ask, why forecast wind speeds? Well, to industrialize the power of the wind, several variables and their timescales must be considered. This paper focused on the second variable in the chart on the right-hand side of the slide, day-ahead scheduling and unit commitment. For wind speeds forecasting on intervals that are less than 48 hours, it is imperative to minimize scheduling errors, which ensures grid consistency, and essential industrial service fees. Fractional ARIMA is a special case of ARIMA PDQ where the differencing parameter D assumes fractionally continuous values in the range of -0.5 to 0.5. The original authors of the paper claim that the fractional ARIMA process is the most accurate when it comes to modeling wind speeds because FARIMA proves to be efficient on models with slowly decaying autocorrelations. ARIMA, however, is favored when the model does not show a slow decay, but rather the decay is exponential. On the right-hand side of the slide, you can find the formulas for fractional ARIMA modeling, where you can see that D is an important parameter that ranges between -0.5 to 0.5. D would typically be 1 or 2 in a normal ARIMA model. To produce the fractional ARIMA forecast, the original paper used the ARIMA from the AUX programming language to simulate and forecast the fractional ARIMA. However, in our replicated paper, we used the ARIMA package in RStudio in an attempt to obtain the same results. Our forecasted models did not look nearly as good as those produced from AUX, and these graphs from an alternative study may explain why. In the graph in the top right corner, you can see that the parameters from R and the AUX matrices are slightly different, and the graph in the bottom right-hand side shows the range from which they may have been different. You can see that R and the AUX Studio do not align exactly, which may relay why our results were different. This did lead us to believe that the AUX programming language is more robust for fractional ARIMA modeling than RStudio. Another reason our results may have been different is due to the data. In the original paper, their data was obtained through a grant, whereas our data was obtained through an open source. Their data also came from 4 potential wind farm sites in North Dakota, whereas ours are from the same site that are not wind farm related. Both our data and their data do contain the months May, December, March, and October, but theirs was recorded on 2-second intervals, which was averaged to 10-minute intervals and then averaged again at hour intervals. However, ours was recorded in 10-minute intervals and then averaged to hour intervals, which may have changed the variance within the data. They also knew the hub height of their anemometer, which recorded the wind speeds, as well as the neg-micon wind turbine. So they applied a power transformation to relay what the wind speeds would have been for the height of the neg-micon wind turbine. However, with our data, the hub height of the anemometer, which recorded the speeds, was unknown. Although we did know the hub height of the neg-micon wind turbine, we did not apply a power transformation because we were unsure what level to apply the transformation, so we just went with the speed or the height that the anemometer recorded the speeds at. They also did have an accurate neg-micon power curve, which was supplied to them, but we had to simulate our neg-micon power curve as we did not have the resources to the data which they used in their power curve. We also analyzed our data with the ARIMA package and our studio, which combines the fractional difference and auto-ARIMA packages, but they utilized the aux-ARIMA from the aux programming language. Neither of the authors in this PowerPoint know the aux programming language, so we did decide to carry out the study with our studio instead. To illustrate the slow decay of wind speed, we have included the ACF plots from our 4 different seasons. You can see that the decay is extremely slow. When we did the ACF plots for the 10-minute intervals, the decay was even slower. So this is the reason why they decided to use the fractional ARIMA modeling to forecast wind speed. The left-hand side of this slide shows the forecast from the original paper, while our forecast is on the right-hand side. It seems that the aux-ARIMA is more robust to fractional ARIMA forecasting than the ARIMA package found in our studio. In both forecast images, the image in the top left corner is going to be May. The one in the top right corner would be December. The one in the bottom left corner would be March, and the bottom right corner is October. The top 2 months are forecasted over a 48-hour interval. This is because the variation in wind speed in May and December is less than that in March and October. The March and October, they were only able to forecast over a 24-hour interval. We didn't notice a difference in any of the seasons for our forecasting, but again, our forecast was not nearly as strong as the forecast that they found. Since our forecast was so weak, we decided to look at the residuals for May, December, March, and October. The ACF plots for residuals do not entirely display white noise, although they are close. And then all but the December residuals seem to have a mean of 0. The model could be better, as is apparent from the forecasting graph shown in the prior slide, but we were not able to make a better model utilizing the ARIMA package in R. In the paper, they did also compare ARIMA versus fractional ARIMA modeling with the wind speed. So we decided to go ahead and look at the ARIMA and see what kind of difference we had here. We did find that the modeling looked almost identical, but the prediction interval does change slightly. It seemed that the ARIMA modeling included more of the variance that was found in the actual test data, but we didn't really notice a drastic improvement in our fractional ARIMA model. Since we did not have the resources to the data used in the original power curve, we simulated a power curve for the neg-Micon wind turbine. We found the information for the formula on a government-sourced website that expressed how they calculate this power curve. It's 1/2 times wind speed density times the area swept by the wind turbine times wind speed cubed. So the power curve shown on the right-hand side of this slide is the power curve that we simulated. This curve has a cutoff at about 31 miles per hour because the data that we used did not have wind speeds above about 31 miles per hour. So you can't see the divot that is expressed in the original power curve that occurs about 35 miles per hour in. This is also because we didn't apply the power transformation, but again, since we did not know the height that the anemometer recorded the wind speeds, we weren't able to figure out the wind speeds that the neg-Micon wind turbine would be receiving. After forecasting the wind speed, you are then able to apply the power curve to the data and estimate how much power output would be supplied by this Negmicon wind turbine. So on the left-hand side, you can see their estimated power output, and on the right-hand side is our estimated power output. Obviously, the graphs don't look the same. They're different data, and the forecast showed entirely different results. But this is the end goal of forecasting the wind speed. And then once you are able to find an accurate way to forecast the wind speed, you can then estimate how much power output the wind turbine will produce, so you can send workers to collect the energy. You can also allocate your resources and accurately know how much power you will be giving to the grid. So this is the primary goal of wind speed forecasting.